Hello everyone, today we have our 9th lecture. And here we would continue our discussion on thermodynamic aspects of corrosion. And in our last lecture, we have come across a relation which is nothing but del G equal to minus NFE, and this relation was obtained from the basic classical thermodynamics as well as electrical work. One side was classical thermodynamics, which started from delta G equal to del H minus T del S, and finally we have got to the situation which is delta G equal to Q minus W prime electrical plus minus Q reversible. This is the relation we obtain, and then finally we considered reversible situation. In the reversible situation, Q equal to Q reversible. So, we got delta G equal to minus W prime electrical. Whereas, on the other side, we have tried to see the work done, which is W prime electrical, if there is some charge flow across a potential difference, and that goes to NF E, that one also we have seen. And from these two conditions, since this is one relation and this is another relation, we got to this relation. Now, this is the work which is the maximum work that is possible when we have 1 mole of substance either coming into the solution or getting deposited on a metal surface. Now, whether this is a maximum work or not, that we can also prove from this relation. Let us say if it is irreversible process, then irreversible process Q is not equal to Q reversible, and also we can see that Q irreversible is, if I put it as irreversible, is less than Q reversible. The heat for reversible heat is more than the irreversible heat. Now, we are considering that the system is going irreversibly, that means there is a spontaneous reaction, a spontaneous process. Now, once we have this relation, then delta G is not equal to minus W prime electrical work. Rather, if this is true, then Q irreversible minus Q reversible, and this Q irreversible is nothing but this in case of irreversible process, is less than 0, because Q reversible is more than Q irreversible. If it is less than 0, then we can get minus delta G is greater than W prime electrical. What it means? That the amount of free energy that is available for doing work, that amount of free energy will not be able to produce the same amount of work what we have noticed in this case, which is reversible. So, in this case there will be some loss. So, entire free energy change will not be available for doing electrical work. Of course, we have seen that the mechanical work part gets cancelled when we start from this. So, this is the maximum work that is possible if the system goes reversibly. Now, once we see this, then we can also derive some useful relation in order to know some of the thermodynamic parameters. Like for any reaction like what we have in our situation, which is copper plus zinc equal to zinc plus copper, which is the relation, which is the reaction that takes place in galvanic cell, which of this cell, and now we saw that the potential difference goes to 1.1 volt, provided the concentration of copper plus is 1, or activity of copper plus is 1, and activity of zinc plus is equal to 1 in the solution of copper sulphate as well as zinc sulphate respectively. This concentration has got huge importance. We will see later on that how the concentration of oxygen in atmospheric condition affects the corrosion of iron. We will see later on when we talk about Nernst equation, because the Nernst equation will tell us why that kind of situation arises if there is a change in concentration of oxygen. Now, this reaction, the complete reaction, of course, copper sulphate plus zinc is equal to zinc sulphates per copper, and this reaction must have some enthalpy change. It also involves some entropy change, and then we know this relation. This is nothing but the free energy change for this reaction, and this free energy change actually gives rise to a potential difference. So, use other relations that we know, those are existing in classical thermodynamics. One such classical thermodynamics relation is del G equal to del V dP minus del S dt. This is a very useful relation. Now, from this we can know that del delta G dt constant pressure is equal to minus del S. Now, we know that delta G equal to minus NFE, then I can get NF, because N and F both are constant for a particular reaction. F is Faraday, 1 Faraday, which is constant. This becomes dt P minus equal to minus del S. So, I am replacing del G with minus NFE. So, both sides this would get cancelled. So, this is the entropy change of a process. Now, if we know the variation of potential with temperature for a particular cell, we can also get the entropy change for that particular reaction. Now, on the other hand, we have this relation which is delta G equal to delta H minus T del S. Now, we have found out a relation like this, which will give me minus NFE equal to delta H minus T, which is of course will become NF dt at a constant pressure. So, del H we can find out as minus NFE plus NFT del T P. So, this is the relation we can get. or we can also get E equal to minus delta H NF plus T del E del T P. This also we can get. So, this is these are two important relations what we can obtain from our understanding on classical thermodynamics, and from there we can also find out this for that particular reaction. Now, we can have an example on this. The example what I would like to put up the problem statement. If I try to see that problem statement, let us say at 25 degrees Celsius for a particular cell like this, AgCl. So, this is the cell if I consider. Now, if these many data are provided, let us say del E del T is equal to 1.8 into 10 to the power minus 4 volt per Kelvin, and cell potential, I can have the cell potential for this cell 0.49 volt, and then one can find out entropy change for 1 mole of silver deposition. In this case, on the right side there will be deposition of silver, on the left side there will be formation of lead chloride. Now, we can also calculate the heat of formation of silver chloride, and the data, another data that is provided is del H of PbCl2 is equal to minus 359,480 joule. So, now first we have to write down the cell reaction, and the cell reaction is half Pb plus AgCl equal to Ag plus half PbCl2. This is the relation. So, where I could see that this is plus, this is 0. So, this is my reduction or cathodic, and here this is 0, this is plus 1, sorry plus 2, which goes to oxidation or anode. Now, the silver will be deposited on that silver chloride plate, that interface. Now, here we have written this equation in such a fashion that I have 1 mole of Ag. Now, when we have 1 mole of Ag, the number of electrons that will be participating in cathodic reaction is, so this is 1. So, N would be 1 here, and accordingly it is adjusted, because once we need 1 electron. So, Pb minus 2E equal to Pb plus plus. So, if I put half, so this becomes 1. So, this 2 would get cancelled, and now we see that the charge conservation is followed. Now, once we have this, now let us go and find out delta G for this particular chemical reaction, which gives me the potential difference, that is 0.49 volt. So, this is equal to NFE, which is minus 1 into 96500, as we have understood from our previous class that 1 Faraday is equal to 96483 or something like that. So, roughly it is considered as 96500 coulomb 1 Faraday and into this much volt. So, which is equal to minus 47285. So, this much is basically my free energy change. Now, once we know that, then we can calculate, we have the data d dt equal to 1.8 into 10 to the power minus 4 volt per Kelvin. From there we can calculate del S. Del S equal to NF del E del T, constant pressure. So, this becomes 1,96500 into minus 1.8 into 10 to the power minus 4. This is also joule per Kelvin. So, this value would be minus 17.37 joule per Kelvin. So, heat of reaction for this particular reaction would be then delta H would be minus NFE plus T del S. How come it comes? Delta G equal to delta H minus T del S. So, delta H equal to delta G plus T del S, and then delta G is equal to minus F E plus T del S. So, we can put those values. This is minus 47285, since this value we have calculated from this equation. Delta G equal to minus NFE, and we have found out that value to be minus 47285 plus, and this T is 25 degrees. So, which is 298 Kelvin into del S we have found, which is minus 17.37 joule. So, this becomes joule. So, then in total if we try to calculate, then it would become 52461.3 joule. And of course, here we are considering 1 mole of Ag deposition. So, per mole deposition. Now, we have to calculate. So, this is our problem statement was entropy change. We have found out entropy change. This is the entropy values. Then we have to find out second problem, heat of formation of AgCl. So, we have found the heat of reaction. So, heat of reaction for any reaction, for example, A plus B equal to C plus D, this reaction if it goes this way, because then our heat of reaction would be H of C plus H of D minus H of A minus H of B. So, formation enthalpy of individual species, reactants as well as products. Now, if we have this particular relation, so then for this we can write as H Ag plus H half of PbCl2 minus H of Pb, of course half, because this half sign is there, minus H of AgCl. Now, if we perform, because this is happening at 1 atmosphere and 25 degrees Celsius, and if we consider that these are pure substance, those cases they can be written as standard values. So, this superscript 0 I am putting because those are standard values, and as per convention, if we have a pure metal, the stable condition, which is solid in case of Pb as well as Ag at 298 Kelvin and 1 atmosphere pressure, is going to be 0. So, this is a convention. Now, we know this value, which is, sorry, there is a minus sign missing. So, minus 52461.3, this is the heat of reaction for that, and then is equal to 0. This is minus, we know this value was this. So, this is half into minus 359480 minus 0 minus AgCl. We can also put 0. Now, then H0 AgCl would be equal to, which is nothing but the formation enthalpy. We can also put formation enthalpy, which is equal to minus 52461.3 minus, this would become plus, and this would become, this is 179,740. So, this is the value. So, equal to around, this would become 7 8 this is 8, then so 179,740 minus 52461.3, 7.877 52721. So, this becomes 127,278.7. So, this is the joule, this is the value of enthalpy of formation of AgCl. So, here we can see that we have not put del value here. We can also put del value, because absolute enthalpy we cannot calculate, we have to calculate a relative enthalpy, which is the difference. So, actually this is nothing but del H0 AgCl. So, this is the formation enthalpy of AgCl. So, we could see that from this relations we can have lot of informations on the formation enthalpy of a species, entropy change for a particular reaction, as well as we can also calculate enthalpy change for a particular reactions. Because E is experimentally determined, E can be experimentally determined, and as a function of temperature at a constant pressure I can also find out this particular relation dE dt we can also find out. So, then entire thing can be chalked out. Now, This is one example. So, we will have problems on this particular aspect, and the TAs will manage that, and of course, I will be also interfering whenever there is a need arising. Now, from these it is very clear that this particular relation delta G equal to minus NFE is basically a kind of fundamental relation in electrochemistry. Now, we have not started looking at what would be that importance of that relation on the corrosion aspects. Now, before we talk about that, we have also stated that the concentration of solution is very important. This is very important. Until unless we have some relation between E and concentration, we will not be able to quantify, and that quantification would be possible if we have a relation which is popularly known as Nernst equation, N-E-R-N-S-T, Nernst equation. In that Nernst equation, we can relate free energy with potential with K P or the reaction constant. So, this Nernst equation will enable us. We have understood this relation, which is delta G equal to minus NFE. We have to understand the relation between these two. This relation we have to understand, and then we will see that how this concentration comes into play. Let us stop here. We will continue our discussion in our next lecture.